Hello and welcome to the next lecture on earthquake resistant design of structures. In this lecture, we would be talking about the ductility features of the building structures. So basically, the design of structures, particularly of the concrete structures, could be classified into two approaches. One is the strength approach and the other one is the ductility approach. We have all studied the strength approach in the classical design of structures, concrete structures. In this approach, we consider the strength of the member, which is a concrete member, to be the limiting criteria for design. For loads which are multiplied by load factors and the material strength, which is classified into the partial design strengths by dividing by partial safety factors, we obtain the strength approach. Now, in this approach, which is given by many codes in India, it's given by IS 456 2000 and the European code EN 1992 1 and 12. These give the strength approach to the design of structures. Now, with earthquakes, this approach could also be used in design of structures. But there is a issue which we'll discuss with using this approach. So there is a limitation to this approach. Next comes the ductility approach. In the ductility approach, the material strength, apart from the material strength, there is one more criteria, which is the energy absorption capacity of the structure that is also taken into account. The ductility approach is based on the material ductility. It's also based on the structural ductility or the member ductility. Now, the ductility approach we'll be studying in detail in this lecture. It's given by IS 13920 2016 code in India for structural design. This code takes into account the ductility approach for earthquake resistant design of structures. In Europe, the code EN 199218, which is meant for earthquake resistant design of structures, considers the ductility approach for the structures. Now, what is the ductility approach of structures? Before we go into the ductility approach of structures, let us recall about the strength approach of structures. In the strength approach of design of structures, if there is a plane frame element as given here and it's under load, for example, the load is the vertical load acting on the structure or the gravity load. Now, when it comes to the stress strain graph of concrete, for example, being a brittle material, what we come to observe that there is a limitation to the strength of concrete. Now, the red line here would show the concrete with lesser grade, and the black line here would be showing the concrete with greater grade. Now, we can keep on increasing the strength of concrete to increase the stress bearing properties of the frame. Now, that would mean, number one, it would mean that we are using higher amount of cement content. Number two, it would mean that we are using we are increasing the member size. Now, in both cases, one, there is an increase in density, and in the other case, there is an increase in mass of the structure. So, overall, in both cases, the mass or the weight of the structure is getting increased. So, if the load is getting increased, stresses are increasing, the section size is also increasing, the mass of the structure is increasing, and there is one more thing that's happening at the same time, that is that the stiffness of the structure is also increasing as we make it more and more dense and more larger in dimension. Thereby, this method would have limitation. First limitation, what we have understood till now, is that there is a limit to the mass of the structure. The second limitation is that there is a limit to which we can go in terms of stiffness, increasing the stiffness of the structure. Because for a lateral load, that would mean larger stiffness would mean larger chances of uh, failing or cracking of the structure. Now, let us look at the steel. We know that steel is a ductile material. Now, why is it ductile? Because it has got a property wherein it undergoes large amount of deformations. Now, these large amount of deformations would give it a beneficial thing when we are using it in the strength approach, like we saw in the last lecture. What was that? That was, once there is an under reinforced structural design, we are saying that XU is less than XU max, wherein the area of the steel that is being used in the structure, that is coming to be lesser than the net area of the concrete that is being used for design. Thereby, the steel that goes into yielding first before the concrete goes into cracking or failure. Thereby, the steel as the material undergoes large amount of deformations. So we are allowing the structure to bend. We are allowing it to deform. We are allowing the structure to undergo curvature, and we are allowing the structure to undergo some strains. Now, this is a material property. So, thereby, in a ductility approach, what we come to know is that there is a energy which is associated with the large deformations, and this increase in energy absorption increases its ability to deform without failure and increases its capacity to not fail. So, coming to this, we can say that ductility of a structural element would depend upon the ductility of the material first. And this ductility is described by ductility being equal to ultimate stress by yield stress. Now, what are we talking about? We are talking about the ultimate stress in a reinforced concrete here and the yield stress in reinforced concrete. Now, this property of ductility being a material property is that it's an ability to undergo large deformations without rupturing. But there are associated things with ductility. Number one, when we are increasing the compression steel content, there is an increase in the amount of ductility. Similarly, when we are increasing the compressive strength, we are also increasing the ductility. Further, there is an increase in ductility with increase in the compression strain. But at the same time, when we are increasing tension steel content, and that has to do with making it over reinforced, the ductility is decreased. Similarly, when we are increasing the steel yield strength, the ductility decreases. And when we are increasing the actual load on the structural element, the ductility increases. So the top portion of this page that you are seeing is showing you that the ductility is dependent on the material properties, and the bottom portion of this page will tell you that the ductility is also based on the member properties, the configuration of steel and concrete, and it also depends upon the loading acting on the structure. Thereby, we can say, as we had described earlier, that ductility is not only a material property, it's also a member property or a structural property. Now, what is a member ductility or a structural ductility? For example, if we are taking a beam and we are loading it with any load, there is a deformation, an initial deformation delta at the yielding point, and then there would be a maximum deformation delta max of the beam, after which it would fail or crack. Now, because this is a reinforced concrete material, we can say we can classify this ductility in form of the curvature, or we can classify this ductility in form of the rotations at the supports. We can also take the ductility in terms of strength. The curvature and the rotation would be dependent upon the shape of the section, while as the strain would be a material classification of ductility, because strains would be between materials at the interface of steel or concrete. Now, the curvature ductility, which is a rough form of determining ductility, would be taken as the rotations at the ultimate, that's at the failure, to the rotations at the yielding point. Now, this could be rotation, or this could be called as curvature. Next is the strain ductility. Now, again, it would be the epsilon u by epsilon y, the strains at ultimate point to the strains at the yielding point. Now, why do we take this as the ductility between ultimate and yielding point? Because it's the deformations, the maximum deformations, they occur in this range. So, how would we measure ductility? For example, if we take a beam which is singly reinforced with the dimensions shown here, the yielding curvature would be phi y equal to Fy by Es into d into 1 minus k. Now, what is Fy by Es? It's the amount of strain. Now, d into 1 minus k, it's giving us the lever arm. Now, this would give us the amount of curvature phi y, as we see in this next figure. Phi u is the amount of curvature at the ultimate point. Now, this would be simply the final epsilon u by c. Thereby, ductility would be phi u by phi y, and we can say that phi u is now that would be equal to phi epsilon u into Es into d into 1 minus k divided by c into fck. Now, this would be the curvature ductility. That's how we can measure the ductility of a beam. There are ductility requirements which are specified by IS 13920-2016 in the context of Indian codes. These are the ductility requirements which are listed here in the rest of the lecture. So, if we make a comparison of IS 456 and IS 13920, what we would come to know is that in IS 456, which is the design of reinforced concrete structures, it's based on strength approach, whereas IS 13920 considers taking into account the ductility approach in addition to the strength approach. So the approach that's used in the Indian context of code for earthquake resistant design is that both strength as well as ductility requirements have to be specified for earthquake resistant design of structures. In IS 456, the concrete grade that is used is M10 to M20, while as in the case of IS 13920, the concrete grade minimum that could be used is M20. Now, to clarify, M10 to M20 in IS 456 is ordinary concrete, M25 to M55 is standard concrete, and M60 to M80 is high strength concrete. Now these all classifications are valid in IS 13920, but the minimum grade of concrete that is to be used is M20. But for structural buildings which are greater than or equal to 15 meter in height and they are placed in seismic zones 3, 4 and 5, the grade of concrete that has to be used is M25. Next comes the requirements of steel bars. In IS 456 you must recall that Fe250, which is the mild steel, Fe415 and Fe500, which are the higher grade steels, are to be used. In IS 13920, as per this classification, Fe415, Fe500 and Fe550, where Fe500 and Fe550 are deformed bars, are to be used for ductility requirements of structures. Now this comes to be classified for all zonal types. Now where do we use the ductility requirements, in which zone, that we would come to understand in subsequent lectures. In IS 456 no irregularity the restrictions are placed on the structural design. In IS 13920 the irregularities that are to be followed in the structural design, and this has to do with the classification given in IS 1893, which we have to study parallelly with IS 13920, wherein the structural irregularities are regulated and avoided. Next, in IS 456, talking about the loads that are considered in the design, there are dead loads, there are live loads, imposed loads, snow loads, wind loads, shrinkage, creep and temperature effects. There could be a combination of all these loads, and there is a certain set of rules of combinations of these rules that are to be followed, along with considering the load factors, which is used in the limit state method of design of structures. Now in IS 13920, the loads for which are considered in the design are dead load, live load and earthquake load mostly. This is the combination that is used in the design once we are designing for earthquakes. Next comes the what are the ductility requirements for beams. We have discussed the ductility requirements for materials. Next we consider the ductility requirements for loads. Third, what is the ductility requirement of beam? In beam, the first thing is the width to the depth ratio. Now this is not limited in IS 456, but conventions are there which illustrate it to be somewhere such that depth is 1.5 to 2 times the width of the beam. Now with IS 13920, the beam width to depth ratio should be greater than 0.3. That is, if the beam width is, for example, 150 mm, the depth would be less than 500 mm. Now this is the restriction that is being placed here, such that the greater the depth to the width ratio, that would make the beam slender, and thereby that is not recommended for ductility design. Next in beams comes the restrictions on the width of the beam. Now in IS 456, the width recommended by calculations and by conventions, not given in IS 456, is not to be less than 150 mm. In IS 13920, there is a restriction on the minimum width that has to be provided in the beams. That is, it should not be less than 200 mm. Lesser the width, that could lead to out of plane bending under lateral loads. Next comes the restrictions on the depth. Now depth has to do with the serviceability criteria because it's associated with deflections. Now, if there is a deep beam, there would be a serviceability problem, and if the span of the beam is quite large, that would surely lead to greater deformations in the beam, and those deformations need to be, or deflections need to be controlled. Thereby, in IS 456, for cantilever, the span to depth ratio is to be taken maximum 7 if the span of the beam is somewhere near 10 meters. When talking about a simply supported beam, this ratio is 20, and for continuous beam, this ratio is 26. Now, like I told you, it's for a 10-meter beam. Similarly, in IS 13920, there is a depth limitation which is based on stiffness and ductility criteria. Now the span to depth limited for all support conditions is to 4. It cannot exceed 4. Now that has to do with the amount of deflections that would occur under a lateral sway condition where the beam is not actually totally rigid. Now this is to control the amount of deflections, and next it's also to redistribute the moments. Now lesser the span to depth ratio, that would mean that more loads are distributed to the supports, and because it becomes like a continuous beam structure, and thereby the distribution and the redistribution of moments occurs to the supports. In a beam, as per IS 456, the effective span is to be taken as the clear span of the beam plus the effective depth of the beam. Now, what is the effective depth of the beam? That we must know that it's taken from the top end of the beam till the center of the tension reinforcement. The effective span could also be taken as center to center distance of the beams. Now, in case of IS 13920, it's same. The effective span is taken as similarly. In case of IS 456, the effective width of the beam is not required here except for T beams and for L flange beams. But in the case of IS 13920 for ductile detailing, there is a concept of effective width of beam which takes into account the support length C and the adjacent beam area C and C from both sides. So overall, the effective width of the beam would be 3C here. Now, what is the purpose of providing this effective width of the beam in case of IS 13920? Because the joint, they are rigid, but they must also become flexible and ductile at the same time. Thereby, the column beam support has to be made ductile, and in that case, we need to relocate or locate the effective width of the beam up till which we provide the ductility in the beam. Talking about the beam reinforcement, there are all types of steel grades which could be used in a single beam when we are talking about IS 456. It could be steel grade of 250 or it could be 500. Now, the bars, they are bundled as per IS 456 in beam reinforcement, and up till or up unto 32 mm dia bars, you can bundle all of them in a single group, tie them up. But in case of 32 mm and greater dia bars, you cannot bundle them into one formation. While as in the case of IS 13920, the recommended practice is not it's not given in the code, but it's a recommended practice that you use single grade steel in one particular beam, and the bar should be minimum 12 mm in a beam. Now that is, it should be 12 mm in dia for a beam. Now that restriction is not placed in IS 456. Next, we are talking about the dimensions of the we have talked about the dimensions of the beam. Now we are talking about the reinforcement and that its detailing in the beam. Uh, for example, in IS 456, the bottom beam, that is uh, a heavier one because it's a tension bar. The minimum steel area that you provide is 0.85 into BD by FY as per IS 456, and the maximum steel area in the tension that you provide is 0.04 B into D. Now the anchoring of these bars of the tension is to be done, and so we add the development length at the end of the beams, which are looking like the bent up portions at the end of the tension bar. Now in the top compression reinforcement, that is restricted in IS 456. If it's a doubly reinforced beam, you can uh, one can anchor the bar just like the tension bar. But if it's not a compression reinforcement, there is no requirement of back anchoring into the body of the beam at 90 degrees. Next comes the stirrups. Now these stirrups in IS 456 are rectangular and they have a hook at the end. Now they are rectangular with around 90-degree bend in at the edge. Considering the diameter of the bar, there is the spacing between the bars is, or the stirrups is, its maximum 0.75 D or 300 mm when we are talking about IS 456. Now coming to the IS 13920, one needs to provide at least 2 bars at the top as well as at the bottom of the compression and the tension reinforcement. Now both are to be anchored properly and the development length has to be added at the ends for both compression and tension reinforcement. Next, if this, that we would be discussing later on, if it's a continuous beam, the some of the bars may run throughout and some of the bars may be spliced or lapped, but they are not to be spliced or lapped at the support ends. Other thing is that there has to be a splicing length that we'll be discussing later on. Here at support conditions, this beam reinforcement has to be actually to be taken into the column, and that we will be showing you in the further discussions. So there has to be an extension of the tension as well as compression reinforcement from beam into the columns, which are the supports at the ends of the beam. Next, the minimum reinforcement percentage that we take here, that is 0.24 under root FCK by Fy as per IS 13920, and the maximum is 0.025. Now there is a particular distance between the stirrups and it has to be maintained. Now there are certain zones in which the reinforcement spacing between the stirrups has to be lesser, and there are certain zones where the stirrup distance could be larger. Mostly it is taken in between 75 mm to 150 mm, the stirrup distance, when we are considering IS 13920. In case of IS 456, if we are taking the stirrups, the minimum diameter of the stirrup, which is a hook shape, it is 6 mm, and the spacing between the bars, the longitudinal bars, has to be maintained, and this should be minimum equal to the diameter of the larger bar, or it should be 5 mm greater than the nominal dia of the aggregates. But the maximum limit is also there. It has to be less or equal to 300 mm for Fe 250 grade steel and it has to be less or equal to 150 mm for Fe 500 steel. In case of IS 13920, the stirrups have to be bent up and a hook has to be provided at the top compression flange of the beam. Now this has to be bent at an angle of 135 degrees, and the amount of hook anchorage in the body of the concrete or the core of the concrete is 6D, equal to 65 mm. The IS 13920 also recommends using cross tie and U stirrups. The U stirrup and cross tie has to be minimum 8 mm as compared to 6 mm in case of IS 456. And this is the formation of the cross tie and U stirrup as recommended by IS 13920.